Hello everyone and welcome back. My name is Mr. Kovald, and in this video I'm going to continue with an introduction to Le Chatelier's principle. So let's get into this. So we gave an example of how you can stress your particular reaction, and you can stress that in different ways, like removing a reactant or adding a product or adding a reactant or changing volume or temperature, and I went over an example to show how that works, right? So one of the things I want to talk about now is that even though the system or the reaction will shift either left or right, either towards reactants or towards products, in order to undo that stress, you can't really get back to where you started. You're not going to get back to the exact same place you were at before. So you're not going to be able to completely undo the stress, the quote unquote stress of the system to get back to the original concentrations, but you're going to be able to at least end up in a better off position than when you were totally stressed in the beginning. So what we mean by stress, again, is not that the system is actually stressed in what we mean by stress, but that we have changed the equilibrium position by adding or subtracting or raising the temperature or anything like that, so that it's no longer at equilibrium. And so therefore the reaction is going to shift, so it tries to get back to that equilibrium, but it's going to reach a new equilibrium. So the reaction is going to find a new ratio of concentrations, so it reaches that equilibrium it was at before. But the ratios are going to be different. The concentrations at equilibrium are going to be different. So you don't quite get back to the original concentrations you had before. So all that happens is that you reach a place where the forward and the reverse or backwards reaction rates are the same. And so remember, when I'm talking about ratios, I'm referring to the KEQ expression, the rate, the equilibrium constant expression. And here is a generic form of that, a more simplified form where it's the reaction, the concentration of the products over the concentration of the reactants. And this ratio is what I'm referring to. So if I change the concentrations of products, then it's going to shift in such a way as to undo that, right? So if I add more products and I increase the concentration, well, it's going to want to decrease that concentration. So this means that this here is going to decrease and it's going to increase this. So that's what I'm referring to as far as changing the ratios. I will talk about this more in detail and talk about the math in another video. So I just wanted to make sure that what I'm saying about new ratios of concentration is referring to the products over reactants related to your equilibrium constant. But more on that in another video. So right now, I'm going to show you a picture or a diagram to explain what I am talking about here. Okay, so here is a diagram of what I was trying to explain. So here's our system. Here's our reaction that we've seen before. So I have N2 reacting with 3H2, and that's going to be in equilibrium with 2 ammonia. So what happens when I add more N2 to my system? So here we are at this level here. This is the concentration of N2 before the stress is applied, and we're at the original equilibrium position. So this is where we're starting. And then I go ahead, I'm going to add more N2. I'm going to increase the concentration of N2 in my reaction vessel. And so what happens? So the concentration goes up. And so now I'm here with regard to the concentration of my N2 during the stress. So I've added my N2. Now the system is stressed. It's not at equilibrium anymore because the N2 has been increased. and the other two players, the hydrogen and the NH3, are still at their equilibrium concentrations, but I've changed the equilibrium concentration of my N2 by increasing it. And so now it's no longer at equilibrium. So now the system has to undo that according to Le Chatelier's principle. And so if I'm increasing this, then it's going to shift this way to get rid of it. So I need more of this to get rid of it, right? So it's going to get rid of what I've added and to create more of this. And so this is going to decrease a little bit too, because I need the hydrogen to react with the nitrogen in order to make more of the ammonia. So what's going to happen is that the N2 concentration is going to decrease until equilibrium is reached uh, at this point here. Now, so during this point, my N2 is going to decrease. My H2 concentration is going to decrease as well because I need H2 to react with N2 to produce more NH3. And so this is going to increase in the process as well. But are we going to go back to the original concentrations? No. So we'll go down as much as we can, but as soon as equilibrium is reached, we've now reached our equilibrium, our new equilibrium concentrations for our reaction. And so here you'll see that there's going to be a small difference between the before and after concentrations of the N2. So before the stressor and after the stressor, there's going to be a slight difference. We're not going to reach all the way back to the original point because equilibrium will be reached again before that point. So you're not going to be able to undo the full stress or the full amount that I added, but you'll be able to reduce it enough to get to back to equilibrium. And so whenever you get back to equilibrium, your concentrations, the new equilibrium concentrations of your reactants and products, are not going to be the same as they were before. And so that's what I was trying to say previously. So hopefully this clarifies what I was saying before. Now let's talk about pressure. Okay, so let's talk about the issue with pressure. So, how does pressure changes, volume changes reflect or tie to Le Chatelier's principle? So, when we change pressure, there's a couple of different ways you can change pressure. You can either add more particles to your reaction vessel, therefore, you're going to make it more crowded. The particles are going to have less space, and so that would increase the pressure because more particles in your container means that more particles are going to be hitting up against those sides of the wall, applying a force, and that force is the pressure that we are referring to when we talk about pressure of gases. So the other way is to decrease the volume. You can shrink your vessel, keep the number of particles the same, but squeeze them closer together. And that's going to increase pressure as well because, again, smaller space means that the particles are going to be hitting up against the sides of the container more often, and therefore the force of those particles is going to increase, and therefore pressure increases. So in these cases, if you are increasing the pressure, this is going to cause the particles to be too crowded or close together. So if you can reduce the number of moles of the gas particles, this will make things less crowded. So if you can in some way remove the number of particles or reduce that number of particles, you'll make it less crowded, and that's going to relieve some of the pressure. Not all of the pressure, but some of the pressure. And again, you're not going to go back to the partial pressures you had before for your reactants products before you added the stressor, but you'll be able to reduce it somewhat. And so what's going to happen if you increase the pressure? Well, the system is going to decrease the pressure by shifting to the side that has less moles of gas. Less moles of gas means less particles heating up against the sides of the container, and therefore you have less pressure. What if you decrease the pressure in your reaction vessel? So if you do something that decreases the pressure in the reaction vessel, this is going to make the particles too far apart. They're not going to be crowded enough in that regard. And so in that case, the system is going to shift in such a way as to go to the side that has more moles of gas. Therefore, if you increase the moles of the gas, then that's going to increase the particles and increase pressure. So let's go over a quick example to show how this works. Okay, let's go over this example here. So back to my original reaction. Here I have, again, nitrogen gas reacting with 3 moles of hydrogen gas, and that's going to produce 2 moles of ammonia, and along with 92.05 kilojoules of energy. So here we have, what the first thing you want to notice is which side of your reaction has the most, more or least moles of gas, right? So we're going to focus on gas because gas is the one thing that's going to be affected by changes in pressure or volume, right? So since they're all gases, then they're all going to be affected. So here I have 1 mole of nitrogen and 3 moles of hydrogen. So that's going to be a total of 4 moles of gas. On the product side, I only have the ammonia, so that's going to be 2 moles of gas. So this has less moles of gas, and this has more moles of gas. So that's the first thing you want to look at when you're dealing with pressure changes. So then let's say we increase the pressure of our reaction vessel. Maybe we decrease the volume. If we decrease the volume, pressure goes up. What's going to happen? Well, in this case, since we're increasing pressure, the system is going to want to decrease pressure. And the way to do that is to decrease the number of particles. So therefore, it's going to want to shift to the side that has fewer particles. So in this case, it's going to shift to the right because the right side has fewer particles than the left. And so that's going to make fewer particles, and that's going to make it less crowded and therefore decrease the pressure. What if I decrease the pressure? Maybe I increase the volume, right? So I increase the volume of my reaction vessel. The particles become less crowded, and so they're going to want to move in the direction that's going to produce more particles so they can up that pressure that was decreased, right? So in this case, the reaction is going to shift to the left. So this side has more particles, so it's going to shift to this side to make more of these reactants and less of these products. So we can increase the number of particles. And so it becomes more crowded and raises the pressure back up. And once again, we should remind ourselves that the pressure, the partial pressures of these substances are not going to reach their original pressures that they were before the stressor was applied. So, but they will go down to a lower level than when applied when the stressor is applied. Okay, so I hope this is helpful. I hope this all made sense and you learned something from this video. If you did, then please, by all means, like the video, share the video, hit that like button right over there. Also, subscribe to my channel, hit that notification bell, and also when you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would like to hear from you. Thanks for joining me and have a great day.